Okay, thank you very much. So, yesterday we introduced the class of rationally connected manifolds. Abbreviated with RC here. And so what we have seen is that, in fact, unirational implies the converse direction is extremely doubtful in general. So we have this, and so we have also the implication Fano. Fano is, of course, not a birational notion. This is a birational notion. And so what did I wanted to, yes. And this implies, as was said yesterday by Yohan Brunebarbe, for example, if X is rationally connected, X unirational, X Fano, this implies, for example, that we have H0 of X and then all the tensor powers of omega 1 of X vanish for any M positive. So this is very strong vanishing. And so, what did I want to tell about this? Yes, and now we have the interesting fact about these rationally connected manifolds is that they permit to split, in fact, arbitrary uniruled manifolds into two parts, essentially the rationally connected part and the non-uniruled part. Essentially, what we have is the following theorem, which is, in fact, the combination of two results. One is by myself and independently by Kolar, Miaoka, Mori, and here by Graber, Harris, Star. For example, if one combines these two kind of results, one obtains the following thing. For any X, there exists, in fact, a unique map, Rx, which goes from X to some manifold Rx. This is surjective here. Here I'm slightly cheating, but not much. In fact, this is not exactly a regular map. This is almost holomorphic. So this is not a problem. This is rational, but in a with very good properties. So I don't need to modify X really, such that we have the following two properties. So the all fibers are rationally connected, and we have two. Rx is not uniruled. Is not uniruled. So we have this splitting result. So this is essentially the idea is just to take a chain of rational curves. You can make a quotient for this, and then you have to show that the base, once you have eliminated all, so you take an equivalence relation between 2 points in X. 2 points are considered as equivalent if they are connected by a chain of rational curves. And so you can construct a quotient. This is a general case of something which I proved, in fact, in a more general situation than earlier times. And so you get something here, which, so that all rational curves are now essentially in the fibers. And the point is to show now that this implies actually that this is not uniruled. And this is a consequence now of a theorem of Graber-Harris star. So this is the, and so the two extreme cases. The first one is when X is not uniruled. Then this is equivalent to say that Rx is equal to X. And this is also equivalent to say that the dimension of Rx is equal to dimension of X. And the second case is when X is rationally connected. And this is equivalent to say that Rx, this is just a point. A point. And also you have maybe a last remark, and we have three. X uniruled is equivalent to say that dimension of Rx is strictly less than dimension of X. So everything of this is obvious, but I prefer to state this. So do you see, if you prefer, you have this X, you have the fibers here, and so you have here Rx, and you have this map. This is X, this is R, and I will just call it R in general. And so this is not uniruled, and here, the fibers here are rationally connected. So this is the kind of splitting, so you can understand uniruled manifolds in this situation. Now, the interesting thing is,
suppose you blow up a point to an abelian variety, what would be the X they blow up?
if you blow this is birational anyway. So look at the abelian variety. So it is not uniruled, and so this means that this is an isomorphism. Rx is isomorphic, and so in this case, this will be, you can choose. Because this is only birationally defined, you can choose. Either you choose the blown up abelian variety, this is better, in fact.
So Rx is a birational. Rx is a rational map here?
This is a rational map, but almost holomorphic, which means that the generic fibers, that the map is defined on the generic fibers. Or if you prefer, if you take the graph, the indeterminacy locus is not surjectively mapped onto Rx. So we have this thing. Yes, and now recall the uniruledness conjecture. So conjecture it says that X is uniruled, should be equivalent to the fact that kappa of X is greater than or equal to 0. Uniruled is minus infinity. Minus infinity, or equivalently, X is not uniruled, equivalent to kappa of X is greater than or equal to 0. In fact, the interesting direction is this. The other direction is easy, but the interesting direction is this, which is the conjectural direction. So we have this property. Now assume uniruledness conjecture here. Now, and so then we have a corollary. The following are equivalent. First, X is rationally connected. We have two. H0 of X, and you can take the tensorized of omega 1 X is 0 for any m positive, or we have a 3. We can make it slightly smaller, sim m. Omega p X is 0 for any m positive, any p positive. And now I will introduce two of our properties. 4, we have kappa plus of X is minus infinity, and then 5, kappa plus, here the plus is lower, X is minus infinity. So let me recall what this means here. Following are equivalent, yes. Recall, kappa plus of X is minus infinity. This implies that for any f from X onto some y, if this is dominating some y, one has kappa of y is minus infinity. And kappa of a point is minus infinity by convention. And also a point is also of general type. So two things, we need these two conventions in general. And kappa plus of X, huh?
What is the condition for?
I'm precisely defining it, yes. This is not recall, this is a new definition. kappa of plus of x, by definition, this is the maximum of a kappa of x L here for p positive, L inside of omega p of x, and rank of L is 1. So this can be defined. So this is here. And so now the remark is this. What is immediate? Is essentially, what is immediate are the following implications. This implies this, this implies this, this implies this, which implies this, and this implies this. This is, everything is easy. Why is it so? For example, just we have to check that if this is true, then this should be true. And so what you just need here is to just consider f star of kz is L. And this is just, this is sufficient. This is a special part, special kind of subsheaf in omega p. So you have this thing which is here. So all of these implications are easy.
So what is
What is?
Z?
Z. Yes, Z does not exist. This is Y. Thank you. This is Y. Thank you. And now, what is, of course, quite important is to have this implication. And this implication, this is given by the theorem, which is here. Because this is here that we use the uniruledness conjecture, because if we have kappa plus of x is minus infinity, this means that for all things we get, excuse me, let us just take the rational quotient here, which is here, and so this is not uniruled. So assume that this is not a point, so we will have, by the uniruledness conjecture, that kappa here is greater than or equal to 0, and this means that now we can lift kz here. And so this gives us in no, yes, I want to say that this is the point, and yes, and this is immediate, okay? Because then we have an y, which is Rx, which has kappa greater than or equal to 0. But here, in order to do this, we need the uniruledness conjecture is used here. So we don't have a theorem. I can tell that there is something which looks like a theorem, but this is, okay. So we have this, and now a second application. Now I'm still assuming the uniruledness conjecture, and so this is the following remark, which is important in some sense. Now, yes, now for any x, we have this rational quotient map, which goes to R, and here, if we use the uniruledness conjecture, and here we have kappa of R, this is greater than or equal to 0 by uniruledness conjecture. So for anything, and so in particular, this means that now this is an isomorphism if and only if kappa of x is greater than or equal to 0. The two things coincide. So this will not appear as soon as we have kappa of x is greater than or equal to 0. And now this means that there exists a J, which is from R. Now we know that kappa of R is greater to 0, and so we can here use the eta k Moishesan fibration. But we don't need to take saturation, in fact. Kappa of R, and here we have J, which is J of R, here. So this is just the eta k Moishesan fibration. So let me recall here that we have rationally connected fibers, and here we have kappa is 0 fibers. So we have these kind of things, And now, if we assume, this means that maybe let it G compose with R from X to X is X0, and this is X1, for example, which is J of R of X, if you want. This is well-defined for any X. Well-defined. This is well-defined for any X. And so do you see what are the fibers? The fibers are essentially things which are rationally connected. If this is a tower of two vibrations, the lower fibers have kappa is 0, and so you have upstairs, you have a rationally connected manifold. So they are in the two primitive types, rationally connected and kappa is 0. So this is a combination of two primitive things. Now the remark is first. 1, 2 is that we have x1 is x0. This is equivalent to say that the dimension, maybe d1 is d0. This is dim of x0, and this is dim of x1. For example, if this is equivalent, we have this because the fibers are connected here. So if the dimension is the same, this is the same thing as saying that the two things are the same. And this is equivalent now to say that x0 is of a general type. This is for a very simple reason, just because the two maps which are here have to, if this is an isomorphism here, if the composition is an isomorphism, both have to be an isomorphism. So isomorphism here, this means that x kappa of x1 is greater than or equal to 0. And the second step tells you that the dimension, that kappa of x1 is in fact equal to dimension of x1. So we have if and only if this is of general type. And now I'm trying here to make a decomposition of any manifold into primitive types. The two primitive types are rationally connected and kappa is 0. And the third type will be general type. So this is the idea, but now we'll iterate. For any k, we can define G R R k, which will go from x0 to x of k here, just by iterating the thing. And so we have now dk, which is by definition the dimension of xk. This is the kth step here. This is decreasing in k. This is decreasing in k. We lose, or we don't lose, some dimension at each step, but because we start, assume that x0, this is x, this is now, this is xn, so this is n-dimensional. So this means that we can't lose dimension more than n times. So this process has to stop at a certain step. So there exists a minimal k less than or equal to n, such that we have xk is equal to xk plus 1, which implies that then xk, this is a general type by the point 1, which is here. And so what is the end result? Now this means, what is the conclusion? The conclusion is that we take this x, we have x1, we have, now we can take xn, which will be xk, because once we have reached the general type case, then the things will not change any longer. So this is the thing, and here we have the, I will call it C star, and this will be G composed with R n times, for example. And so what we know that this is general type. Maybe I will take xn, which is xk. This is general type. And here, what are the fibers? The fibers are iterated towards by fibrations of rationally connected, kappa is 0, rationally connected, the kappa is 0, and so on. So you have this kind of a process. And so what can you show? This implies, this is an exercise, if you want. Exercise. The fibers, and I'm sorry for the fibers of C star. I will call it the weak core map. This is not interesting in itself. I would like to say, we will see why, but this is an approximated version of a right object. The fibers of C star, which is equal to J composed n times, are very weakly special. Very weakly special meaning, which means have no surjective map, rational dominant if you want, onto any Z of a general type with a dimension of Z positive. So very weakly special means this property. Excuse me, for the fibers, we can check that they are very weakly special. And if we use, in fact, the uniruledness conjecture, conversely, if we have, this is also an exercise, that if we have something which is very weakly special, then we can decompose it by this succession of maps, canonically defined. This is not very difficult to show, but you have this, for example. And so this means that what is this weak core map doing? This is splitting our X into things. We have a splitting map. Maybe I call X goes to Xn, for example. And so this is the weak core map. So fibers are very weakly special, and base is general type. So this is, if you prefer, this is a kind of splitting which is similar to this one, but we have replaced here the fiber rationally connected by very weakly special and this general type. So this seems to be pleasant, a good thing, but actually this is not. This is in fact not good at all, and I will explain you why. This is now the remark is this. We shall take always this usual, very simple counterexample to some things. So the example is this. Example is this. We have already seen this. We take X prime. This is E cross, maybe I call it F, I don't remember. F cross C. And here we have a Q, which is 2 to 1 et al. Over X, which is, yes, X prime divided by Z2 here. And we have a B, which is P1. And here we have a projection map to C. And here we have this ramified. This is 2 to 1, but ramified. And so this is G X prime. And so this is Jx here. If we want, so remember that F is elliptic, C is hyperelliptic, this is hyperelliptic, and so we had this, I don't remember, theta maybe, and here we have a translation of order 2. And so we have this, and so we have the cover, and this is P1, and this is C, C divided by theta here. So this is ramified, but this is here et al. And so now, if we apply this weak core map on this side, this will stop at we have C, this is how to say, yes, this is X prime 1, because the first step, there is no rational quotient map appearing here because this is a kappa. So we just need to take the eta kappa vibration, and this is the eta kappa vibration, and this is the eta kappa vibration because it is elliptic, and so the kappa is 1 here, so kappa is 1 here by preservation of et al. Property. So this is also the unique elliptic vibration, so this is J, and so this is on B. But now this is X1, and because this is of a general type, and this is also X prime 2. And so this map here, this is the weak, this is C star for X prime. And now what is C star now for X? This is very different because we have Gx, this is also G composed with Rx, for example. So this one, this B, this is X1. But now, because we have P1 here, this goes to a point. 1 point by R. B, if you take P1, you just have 1 point. And so this means that the two things are completely different here. Do you see? This is not compatible with even with an et al. Cover. And so this means that here, excuse me, yes, you don't see this. This is very weakly special. This is very weakly. Yes, excuse me, yes. This one, this X is very weakly special, but X prime is not. Because just it has this map. So do you see? So this means that a very weakly special is bad behaved, and so this kind of thing, which is actually what the MMP, usually people in the MMP claim, that you have this kind of building blocks, and so, but this doesn't work without some changes. And we shall see what are the changes. And so, yes, we shall see later that we will introduce another version of a core map, the true version of a core map. And so this will be stable by et al. Covers, which is not an easy thing. And we will have a similar decomposition. But now the decomposition will take place not in the manifold category, but in the orbifold category. So these are the changes which have to be made. Yes, conjectures for primitive manifolds. One doesn't need to make big, to have much creativity. We will just plug in what is expected in the case of curves. So in the case of curve, we have G is 0, G is 1. This is equivalent for curves to potential density. potential density, and we have G, this is equivalent to modelicity. And so the conjecture we are making is just the following, that modelicity, this should be equal now to kappa is n, so this is the general type. But this has been, this is due to long, and now we claim that we have implication, that if we have kappa plus is minus infinity, or kappa is 0, we have this implication. This should be implication. So the conjecture is here on this side, and this is quite open. I don't have time to give examples which are known and so on. But essentially, just to be very short, for arithmetic geometry, the only basic cases which are known are for unirational or rational manifolds, or for subvarieties of abelian varieties. And the group law is essential in the proofs. Now, if you are on the analytic version, you have some more situations, but I don't have time to give them. But you have more situation because the situation is easier to handle. So we have this one, and so this is not very surprising. But now we want more. What about the implication for potential density? Yes, potential density implies what is, we want to have an equivalence, and for some geometric notion here. And so this geometric notion, I believe, is the following. Did I forget to say something here? Yes, yes, just a small remark here. If we take, let us take X, which is of the form Y cross Z, for example, and here Y, that Y, for example, has kappa plus of Y is minus infinity, and here we have kappa of Z, for example, is 0, for example. Let us take such of this type, and then this is not primitive. Is not primitive because we have kappa of X is minus infinity in this case, and we have kappa plus of X. This is now, this is kappa plus, in fact, this can be checked, kappa plus of Z, which is greater than or equal to kappa of Z, and so which is greater than or equal to 0. In fact, conjecturally, this is equal, but we have this property, and so this is not a primitive. It doesn't fall in any of the classes in the primitive classes. So this means that we need really just the consideration of products means that if we want to have to invert this thing, we will have to consider more general manifolds than the ones which are here, which are primitive. Primitive is not sufficient. So this is a very simple remark. Huh? Pardon? No, 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 no. Yes, no, in this situation, essentially, if, let us assume that we believe in the uniruledness conjecture. For example, this implies already that even without the uniruledness conjecture, actually we showed this, the fundamental group of this is trivial. Fundamental group is trivial, so you have only this one. And so you will still have something which will have kappa is minus infinity, but the only étale covers you may have, they will come from this. The étale covers don't appear here. Thus, let me write this. The class of potentially dense manifolds is strictly larger than the primitive. Primitive non-general type. Actually, it contains the products. It contains products. So this is. So this, we certainly have to consider something more general. And now let me give the definition, and I will try to make it understandable. So special manifolds. So the definition is that X is special if for any P positive, any L which is inside of omega P X, which is rank 1, one has kappa of X, L is strictly less than P. So the essential thing is this. Not. So this is the definition. So this is very easy to state, slightly less easy to see exactly what it means. But at least I will show some things which are clearly weaker statements. So let me remark first. This is a birational notion plus étal. So this means that if you have something which is special, if you take a finite étal cover, then this is again special. This is difficult. This is difficult. The étal, this is difficult. At least I don't know any simple proof of this. This is very surprising. Probably that this is difficult. Usually, étal covers, this is easy to deal with, but here for this property, this is not. Birational and étal. And now, let me some remarks. So, one, if X is of a general type, pardon? So this means the following. Yes, assume first that we have some F which is surjective onto X. Special here implies special here. This is easy. Even if you have different dimensions, this is okay. But, this is easy. This is easy. But to go in the other direction, this is of course completely wrong in general. But if F is finite étal plus X special, then this implies that X prime is special too. So this is the meaning of being an étal property. Now, if X is of a general type, then this implies then that X is not special. Just take, I take Xn, just take P is n and L is Kx. This will contradict because Kx, this is just omega nx here in this case. So this is certainly a line subbundle of omega nx. So general type implies not special. General type means and with n positive. I take n positive. Now something which is a little bit more general and not more difficult. If how should I formulate? Yes, xn X very, X special implies very weakly special. Why is it so? This is always the same kind of argument. Implies very weakly special. Proof, this is very easy, but I give it because this is important to understand how it works. So assume not, then we have X, which goes to Y, which is of dimension P positive here. And so we just take L. L is F star of K, Y, for example. So we have, this is sits inside omega P X now, and we have kappa of X L. Now this is kappa of Y KY, which is kappa of Y, and by assumption, assume not, and so with YP of general type, so this means that equi IP is P, and here this has to be equal to P. So we get a contradict X special. So this is not complicated, but you see, we have just to choose very special subsheaves here inside of omega P, those coming from certain vibrations in order to get a contradiction. But here, this is a very important point, is that we don't only take inverse images of this, but more general objects. So this will be the difference. And now we have 2 plus. Now if X is special, this implies that X is weakly special. Let me recall, this is the same definition as given yesterday by Yohan. And so weakly special means any étal cover of X is very weakly special. But now, since we know that X is special, that this is stable by taking a finite étal cover, if we take any finite étal cover, this is again special, and so it has no map. It is very, very weakly special. Any finite étal cover is very weakly special, and so this means that X itself is weakly special. And so we have seen that this example, for example, is X prime, for example. This is weakly special. Weakly special, and so this is very weakly special, but not weakly special. It's not weakly special because it has a finite étal cover, which is not weakly special, not very weakly special. So we have this kind of property, and so as you see, we have this kind of implication, but now the reverse, the converse is false as soon as n is greater than or equal to 3. So you have the first examples were given by Bogomolov-Chinkel of threefolds, which are weakly special, but not special. For surfaces, we have the two things are equivalent. This is not very difficult to show by classification. No. Pardon, excuse me. Weakly special? X prime very weakly special. Oh, but just because this is of general type. So this is not very weakly special. X prime. X prime. Why is X? X prime weakly special? No, it's not, because it has a finite étal cover, which is not very weakly special. I'm sorry, with special, very weakly, and very weakly, this is certainly completely. Huh?
Is that X prime is weakly special? No, it projects to something of general type.
It is not very weakly special because it maps. It has a map onto something which is of general type. So. What? Is not. Yes, is not weakly special. There is a knot here, but the knot is connected with this. Sorry. Excuse me. Okay, thank you. This was connected. What did I want to tell now? Yes, some examples now. First, curves, so we are not very surprised. If we have G is 0 or 1, this is equivalent to say that X is X with is G is special. So the special curves are exactly these ones because the only case, only P is 1 occurs. And we have no choice, L is Kx. So we have, this is the only possibility. We have two. Now this generalizes as follows, that X is rationally connected, implies X is special. And so this is because we have seen, because this implies then actually what we have called the kappa plus of X is minus infinity. So this is a very strong form even. In fact, in this case, we have kappa, we have a stronger property that kappa of XL is minus infinity for any P positive and any L inside of omega P X. So we have a stronger property, which is here. Now we have 3. If kappa of X is 0, this implies now that X is special. At least we can see that special manifolds, they contain the admissible, potentially dense primitive manifolds. X is special, and so this is implied. This is not an easy theorem because it uses, in fact, a solution CNM orb, I mean an orbifold version of a CNM conjecture, and in fact the special case treated by Frederic, but in orbifold situation. I will tell more in orbifold situation. So we need this an extension of this CNM conjecture and the solution given by the partial solution given by Frederic. So this is we have particular cases. Cases which are easier. Kx is trivial, which is implied by Kx torsion, and which is equivalent to say that C1 of X is 0, or if you prefer, more numerically, kx is numerically trivial. So if we have this, then we can get a much easier solution than in this case. And a very particular case is x is an abelian. Abelian variety. In this case, this is particularly simple because the tangent bundle itself is a trivial bundle. So you can't have a larger. So, but actually something much stronger is expected in this case, and this is a conjecture that we should have, in fact, kappa plus of x is 0. This should be implied, but kappa of x is 0. So this is a conjecture. So is this true? So this is a much more restrictive than saying that x is special. So in particular, this means that x can't dominate. This says, in particular, for example, that x can't dominate, if kappa is 0, can dominate something of a dual type. But this says that it can only dominate things which have kappa less than or equal to 0. So this is much stronger. But this is implied actually by a complete solution of CNM OR, but this is a conjecture. So we have this kind of example. So this contains. So now another remark, for example, is that for any k, for any n, say positive, and k which belongs to minus infinity, 0, 1, n minus 1, and n. But here I will erase these two things here. So if I exclude these two, n and minus infinity, there exist xn and yn special, and this is not special with kappa of x is k and kappa of y is k. So this means that each time you are not in this particular case where we have kappa is 0, we know that in this case this is special. In this and n, we know that this is not special. So for example, the situation is solved here in this situation, but for all the other cases, the Kodaira dimension will not determine specialness because you have two properties. I will not give examples, but it's not too difficult to give examples. And now, yes, so maybe I can take the case of surfaces. It's possible using classification to show the following, that x2, so this is a surface, is special. This is equivalent to the following two conditions. Kappa of x is less than 1, and we have pi 1 of x is virtually abelian. And this is equivalent also to say that x2 is weakly special. But as we have seen before, not very weakly special. Very weakly is too weak, but weakly special is okay, for surfaces only. And so we have this. In particular, this means that now if you look at this, this is invariant by deformation. This is certainly invariant by deformation. So this means that for smooth surfaces, being special, this is stable both by deformation and by specialization. So you have two things. So in higher dimension, this is completely open, even for n is equal to 3, for example. So these are essentially the example. No, I would like to give an example of a completely different nature. It can be special or not special. You just take a product. P1 cross something of a general type. Take always the most stupid examples, and they will work. I'm sorry, but yes, the simplest example work.
Is that an open question or
Open.
open question?
I conjecture this should be true, but okay, conjecture if you want. N. Conjecture. You can even ask something which is more dangerous. Is a specialness, for example, a diffeomorphism invariant? I mean, is it just if you have two projective manifolds which are diffeomorphic, if one is a special, is the other special, for example? If this is open for any n larger than or equal to 3. Yes. Yes. 2 is known, but because the description is very simple. Just pi1 determines the thing. And here, so I will stop. And in the next talk, I will explain why. The difference. Between, yes, weakly special and special. And this is due to some orbifold or saturation considerations. And I will be more precise considerations. Actually, I hoped I had the time to explain this, but I don't have. Okay, sorry. Stop here. I think I'm finished, yes. I don't have time to say. Maybe if I can take 2 more minutes to explain something, which is not this, but something that about the question you raised yesterday, just to explain a little bit something. So let me say that I have, in general, L line bundle on X. When we say that this is a definition, that L is pseudo-effective, and I will take a certain definition, if LCT is not pseudo-effective. This is easier, actually, to say that something is not pseudo-effective. Not pseudo-effective is if there exists here CT such that which is less than 0, where CT, this is a covering family of curves, generically irreducible. So if you have a family, a covering family of irreducible curves with, then we say that L is not pseudo-effective. And now the remarkable theorem, which is due to Miyaoka-Mori, says the following. It says that Kx not pseudo-effective is equivalent to X is uniruled. So what does it mean? In one direction, if X is uniruled, this is very easy because if you have a covering family of rational curve, then their intersection with the canonical bundle is immediately negative, less than or equal to -2 even. But this is easy. You can make this as an exercise. So this direction is easy. The other direction is you can see how non-obvious it is because you start with a family of a covering family of maybe of very high genus curves, but which have a negative intersection with the canonical bundle. And so you have to produce out of this covering family of rational curves, which are the most difficult, the most rare curves. And so they do this using characteristic bend and break technique and characteristic P arguments and Frobenius lifting. And so this is a very remarkable theorem. So you have this. And now the other thing is that now we have another theorem, which is due essentially to Buxon, de Mailly, Pound, and Peternel, and which says actually which says that L is not pseudo-effective. This is equivalent to say that for any A ample on X, we have there exists MA positive such that H0 of X then ML plus A. This is 0 for any M which is greater than or equal to MA. So we have the equivalence between this and this. So in the language of former Italian geometers, this means that, but for the canonical bundle, essentially that adjunction terminates if L is Kx, adjunction terminates. So if you want, even if you have a very ample line bundle, so your line bundle is sufficiently negative to kill the sections of A when you take a sufficiently large section. And now, what is the difficult thing? The conjecture. The conjecture now is that kappa of X is minus infinity. Does this imply then that Kx is not pseudo-effective? So this is the conjecture. So if you want, if solving this conjecture implies this is equivalent to uniruledness conjecture. If you want, you can make this equivalence here. And so you see, here we start just with the absence of sections, but this doesn't tell you that you will be able to kill, actually. And there are very easy examples. These are not very interesting examples, but nevertheless, if you take L, which is numerically trivial, or C1 of L is 0, but L not torsion. Not torsion, this implies, for example, that kappa of L is minus infinity, but L is not, is pseudo-effective. Pseudo-effective means that it is not pseudo-effective. L is pseudo-effective. So this is very easy to check this. There are more interesting examples, but you have this, for example, you see that this is a delicate thing. So I'm stopping here.